Hello students, welcome back. Let us resume our discussion in section 4. Previously, we went through the derivative rules, the constant rule, addition rule, and coefficient rule, and then the power rule. We went through some examples associated to those. Here's an example. All these are power functions, so we can use this power rule. Well, all except one. This is constant, so the constant rule applies. So that one becomes 0, so that one just drops out. And otherwise, they're all power functions, so power rule applies. But we can do this term by term separately and add them up because of this addition rule. And then you can do this coefficient separately by this third rule, coefficient rule. And the consequence is this. X to the third power became 3x squared. 3x squared here became 6x. And then 4x became just 4. And then the constant just went away. That's 0. Do not change the order. If you change the order, you're losing the justification. Same here. You can change these radicals into the power form like this. Do some exercises. It may take some effort, and it may be a bit time consuming too if you're doing this for the first time or relatively new to it. And then by the time it is done, you get exhausted. And do not apply the power rule, which means you're not taking the derivative in a derivative problem. That's not going to give you a lot of credit, right? And then for each power function, apply the power rule. For each of them, apply the power rule. And in this case, you're multiplying by negative power, so sign change also follows. Power rule, and then the power rule. The details is left to the students. Okay, we just reviewed power rule again because it's important. Now, there are two more rules. Exponential function, the natural exponential function remains the same. And the natural logarithmic function becomes 1 over x, or equivalently, negative first power. 1 over x and x to the negative first power are the same. And me personally, I prefer the power form. I like this one better, x to the negative first power. Our textbook author prefers 1 over x expression. Both are correct. Just do whatever you want to. Me personally, I like power form better, negative first power better. And as for some extension of this rule, here we go. If you have arbitrary base a, then multiply natural log of a and divide by natural log of a. But let's consider this a bit later when we learn chain rule next week. For now, let's stick to these two. Okay, here we go. A very, very nice problem on exponential function. Okay, all right, let's begin this. And let's take a little bit bigger font. And then let's put some space in between. Okay, ready to go? Let's see. E to the x power, can you take the derivative? Exponential function, okay, looks like that's ready. X to the e power, can you take the derivative? Which rule is it? That's a power rule, x to any power. N does not have to be an integer. It's just e in this case, so that's ready as well. How about ex? Is this ready? It's again a power rule. Power of 1. E is just a coefficient, and the power of 1, nothing is there, then 1 is hidden. Now, x over e, how about this fraction? Did you go through any derivative rule that involves a fractional quotient? No, not yet. So this has got to be something different. Don't look at it as a fraction, but look at it as 1 over e times x, or more precisely speaking, first power so that you can use the power rule. Okay, that 2 is ready. Now the hardest of the bunch, e over x power. What's the derivative rule associated to this? Well, don't look at it as a fraction. Change it into a power. 1 over x is x to the negative first power. So rewrite it as x to the negative first power. And then finally we are ready. Okay, let's take the derivative. The derivative of e to the x is same, e to the x. Right here. So that's purple. And then x to the e power. We have this rule here. So multiply by the power e times x, and then subtract 1 from the power, e minus 1 power. So that's brown. Next, ex. 1 is hidden, so multiply by 1, which won't change anything, and then subtracting 1 from the power, we have 0 power. But nobody writes like this. 0 power is just 1, so just e. That's sufficient. That's green. Next, how about this one here? Multiply by 1, and then subtract 1 from the power. So again, we get 0 power, but 0 power is just 1, so nobody writes like that. So blue. Okay, we are up to here. So far we had been using this rule once, and then everything else is this. Next, the red one here. Multiply by power, so that's negative 1, so negative e x to the negative second power, because we have to subtract by 1. So that's red. And then this sign change also came from this derivative computation. And finally, the derivative of this constant is 0. This is just a constant, no x here, e to the e power. It's not exponential, it's not power, it's a constant. So constant, so you don't really have to write it. You can throw that away if you want to. Anyway, this completes the derivative computation. And in this case, it is very, very important you do not change any order. You know, the addition is commutative, so you're free to change the order, but you can change the order in simplification process. When you're taking the derivative, no. You have to justify each term. How many terms are there? 1, 2, 3, 4, 5, 6 terms there. So you can use 6 separate lines to get each of them, and then put those two together, all those together, at least 7 lines for this problem, at least. Quite possibly more. You write like that, or you do it this way so that everybody can see which term comes from where, and then everybody can easily see the justification, how the derivative rules were applied, especially this one. So this preparation is necessary, and in the answer, the order is absolutely necessary. If you switch the order, if you do further simplification or things like that, then that's not going to give you any credit. Quite possibly 0 credit, maybe 1 or 2 credits, because I may have to separate those answers with the people who are just giving up, or maybe just 0. I mean, I'll show you. If you just blindly copy the calculator's computation, this is what you're going to get. I did this computation a bit earlier to check how these web-based computer algebra systems are working. So the derivative of e to the x minus x to the e power plus ex minus x over e plus e over x minus e to the e power, same problem, and read it, and that's what this math way calculator spat out. Now, where is the justification? None whatsoever. There's no justification. So 70% of the problem is just completely gone, no justification. And as for the answer, well, 30%, if you're really lucky, you're gonna get 3 out of 10, but I doubt it. Just copying blindly from somebody else's work, that's a plagiarism, isn't it? So 0 credit probably. Let me emphasize again, do not change the order. Addition may be commutative, yes, but you can change the order after the calculus. After the derivative computation, if you're simplifying, now you can do that. But when you're using calculus, when you're using the derivative rules, you must keep the same order so that you can justify each term, one term at a time. Do not change the order. How many times did I emphasize this? I cannot count anymore. Do not change the order. Do not change the order. Okay, one final problem here. Derivative of these log functions. Okay, before taking the derivative, better work out some log. Log of y plus log of y squared, so that's 2 log of y. Log of y cubed, so 3 log of y. So this entire thing is actually 6 log of y. Okay, now I'm ready to take the derivative. F prime of y is 6 times y to the negative first power. Or if you prefer, F prime is 6 over y. Me personally, I like the power form better. Our textbook author prefers the fraction form better. The majority of the students do it this way. That's what's my experience. Me personally, I like the power form better. Natural logarithmic function is relatively less of a deal at this moment. Natural exponential function, on the other hand, is a big deal. And the power rule, that's really a big deal. Let's see, do we have enough time for another example here? No, we'll do this in a separate video.